In this video, I'm going to focus on the common math concepts that you may run into in any algebra-based physics course. Let's start with conversions. Length, you want to be in meters, mass in kilograms, time in seconds. So if you started in any unit that is not those three, you want to convert your way back. Now these are just the three most common conversions out there. You certainly could run into more. I'm just saying you better know these three. Prefixes, they're in the green boxes in the middle. Their symbols are to the left. Their conversion factors to the right. We use these as an alternative way to write more complicated numbers. So if the example is 6.4 nanoseconds, that's a very small number. You can look at the conversion factor and write it as 6.4 times 10 to the negative 9th seconds. You can also use the symbol and write it as 6.4 ns. Scientific notation, if the power is positive, like the 6, that corresponds with a number larger than 1. If the power is negative, like the negative 4, that corresponds with a number smaller than 1. Dimensional analysis, just more complicated conversions, trying to do 2 or more units at the same time. In the top example, we're trying to go from kilometers per hour into meters per second. So 2 examples here. If you want to try either of them, I've put the answers in the attached worksheet. Geometry, starting with circles, know the difference between a radius and a diameter. To calculate the circumference, use 2 times pi times radius, the area as pi times radius squared. For rectangles, just know the area is base times height, and triangles 1/2 base times height. Trigonometry, specifically with right triangles. First important step would be to label your sides as opposite, adjacent, and hypotenuse. From there, if you know 2 of the 3 side lengths and you're solving for a third, use Pythagorean theorem. Next, your trig functions. This is how you get the angle involved. You may have heard of these as SOHCAHTOA. It just helps you connect each trig function with its corresponding sides. So if you're given a problem where you're given the adjacent side and the hypotenuse, and you're solving for the angle, we'd want to pick the cosine function because that's the one that connects those 3. Algebra, first just solving for a missing variable. In each of these examples, you're just looking for the value of x. Next, systems of equations, 2 equations with the same 2 unknowns. In this case, you're solving for the values of a and b. Then the quadratic formula, an equation that has a squared variable, a regular variable, and a number, and we're trying to find the value or values of the variable x. If you want to try any of these, I've put their answers also in the attached worksheet. Graphs, specifically linear graphs, we start by analyzing the equation y equals mx plus b. I'm just reminding you what each of those 4 letters mean. And then know that graphs come up in your lab a lot, so it would be important to know the difference between an independent and dependent variable. Independent variables are the ones that you have pre-selected measurements for before you even started the lab. Those are graphed on the x-axis, and the dependent variable is what you've recorded as the result of doing the lab. That's graphed on the y-axis. Sticking with graphs, let's talk about mathematical models. This is a way to take the y equals mx plus b equation and turn it into a more useful physics equation. To get there, I've just made up a graph using p measured in L on my y-axis and j measured in v on my x-axis. I've also added some numbers to this graph. First thing we want to do is get rid of the variables y and x. They're more specific to a math equation or math class. We have actual variables in this graph, and we should use those. So I'm going to sub in p for my y, and I'm going to sub in j for x. Because this graph has numbers, I can solve for m, the slope, and b, the y-intercept. If I do so, the slope comes out to 0.5. The units would be L over V, rise over run, and my y-intercept is 1. And I'll use L as the unit because that's what my y-axis is measured in. So this is a better physics equation because I can plug in any future value of j, and it would spit out for me the value of p. Percent error is just a way to show accuracy. The equation's in the middle of the screen. It requires the value of the actual and the experimental, both of those. So the actual value, just know that this is the ideal value. It's if conditions were perfect. Your teacher may have told you this before you even started the lab. Maybe she said, hey, the number's 10. That's what you guys are looking for. Then you go into the lab and you run the experiment with your lab group, and maybe you have found that it comes out to 9.7. So this is your experimental value because you recorded it as the result of doing an experiment. We plug these into the equation. We take the absolute value, which are these vertical bars. We multiply by 100, and it would spit out for us the percent error. Know that a very small number, like 1%, that's a low amount of error. You probably did a good job. If your number comes out to 99%, that's a lot of error. You might want to go back and check some of your calculations. Significant figures, just know every teacher is different. I'd recommend you be reasonable. If you're dealing with a very large number, you can get rid of the decimal because it doesn't change the number that much. If it's like 10.31, you can drop the 1. It doesn't change the overall number very much. Whereas if your number is 0.31, I would just keep it as is because the number is so small. Any change you make to it would change the number a lot. Finally, your graphing calculator, make sure it has trig functions, sine, cos, tan, and always have your calculator in degree mode for physics classes.